Assalamualaikum and hi everyone. Our main topic for this project is solid state NMR studies of the structure of graphite oxide. The principle of solid-state NMR is that many nuclei have spin and all nuclei are electrically charged. It is because if an external magnetic field is applied, an energy transfer is possible between the base energy to a higher energy level, generally a single energy gap. The energy transfer takes place at a wavelength that corresponds to radio frequencies, and when the spin returns to its base level, energy is emitted at the same frequency. The signal that matches this transfer is measured in many ways and processed in order to yield an NMR spectrum for the nucleus. Graphite oxide has been prepared in 1860 by oxidizing graphite with potassium chloride or nitric acid. The various structural models of graphite oxide that have been proposed differ with the nature of oxygen-containing functional groups. Different models were in the last 60 years depending on the characterization technique prevalent at the time. It is known that graphite oxide preserves the layer structure of graphite, but the conjugate bond structure is lost. Experiments using various techniques have established that graphite oxide contains different amounts of tertiary alcohol groups, ether groups, and double bonds, as well as enol and ketone groups. The derivatives of graphite oxide were prepared in order to distinguish different functional groups and to determine whether the double bonds are aromatic or non-aromatic. Spectra of chemically treated graphite oxide have provided additional information. As a result, we were able to reassign the 13 carbon resonance, 60 and 70 ppm, and demonstrate a number of new structural features. Next, there are three objectives in this project. First is to determine graphite oxide spectra and its derivative. Second is to determine the contact time of graphite oxide and its derivative. Third is to identify tertiary alcohol group, ether groups, and double bond groups using carbon-13 NMR line at 60, 70, and 130 parts per million.
I will proceed by presenting the methodology used in this research. There are three main parts to this process. The first part involves the preparation of a sample. 6 samples must be prepared. The first one is our primary sample, which is graphite oxide, and the other 5 samples is a graphite oxide derivative. To prepare the graphite oxide, the parent sample undergoes an oxidation process using sulfuric acid or potassium permanganate. After that, the sample was washed using 5% aqueous hydrochloric acid and was dialyzed for 7 days in the dark to make sure the solution was free from sulfate and chloride ions. During the dialyzing process, dialyzing water needs to change accordingly. After that, the sample was dried to remove the adhering water and crushed to powder, and it was dried again at room temperature. Now, we move to preparation of derivative of graphite oxide. The first derivative is graphite oxide attached to Da. 0.25 gram, our main sample, was treated with 1 gram maleic anhydride in 10 ml of toluene. Second derivative, graphite oxide attached to deuterium, and then graphite oxide was exchanged with 90% of deuterium and 10% of water. For the third derivative, graphite oxide attached to base, 0.24 gram graphite oxide was treated with 0.68 gram sodium ethoxide in 10 ml ethanol with air being excluded. For this process, supernatant is removed using a syringe to prevent contact with air and washed several times with ethanol, and then it's dried. For the next derivative, graphite oxide attached to base water. It's made by washing graphite oxide base 3 times with ethanol and then washing it with water. Lastly, derivative of graphite oxide attached to ether. Graphite oxide attached to base was treated with 0.314 gram 1,2-dimethyl ethane in 8 ml dioxane. Adhering solution extracted with chloroform, and the sample was washed with water and dried under vacuum condition. Part B is preparation of this compound. 16.3 ml methyl chloride added dropwise to a solution 1,2-ethanediol in 40 ml of chloroform and tetrahydrofuran mixture. And then 14 ml of pyridine was added to the solution. The solution was added to ice cold mixture of 100 ml water and 35 ml hydrochloric acid and extracted with 50 ml of chloroform. After being extracted, it was washed with water and dried over sodium sulfate. After that, the solvent removed under vacuum condition and then colorless crystal produced. Part C is solid state NMR. After the preparation of the sample was tested using solid state NMR. Carbon 13 and proton NMR was recorded using the chain magnetic CMX400 spectrometer, and then it's operating at 100.6 and 399.9 MHz.
I will explain about the result. Figure 1 shows high-power 1H decoupling of GO and its derivatives in the 13C blush decay spectrum. Next, Figure 2 shows standard 1H 13C CP MAS spectra of GO and its derivatives obtained with a 4 ms contact time. Figure 3 shows dipolar dephase 1H 13C CP MAS spectra of GO and its derivatives. The acquisition latency is 50 microns. Next, Figure 4 shows short contact time GO and its derivatives 1H 13C CP MAS spectra obtained with a 50 microns contact time. Figure 5 shows in the COH and COC groups, protons may be near to carbons. Next, Figure 6 shows in the COH and COC groups, carbons may be near to protons from intercalated water molecules. And last, Figure 7 shows spectrums of GOs and its derivatives 1H blush decay. Next, for the discussion, in Figure 1, there are 3 lines in the proton decoupled 13C NMR spectrum of GO, which are located at about 60, 70, and 130 ppm. The GO-DA spectrum is no different. It is known that the first 2 peaks are caused by tertiary COH and COC groups, and the third peak is caused by CC double bonds. Figures 2 until 4 display the conventional dipolar dephase and short contact time CP spectra of GO and its derivatives. The result of all 3 experiments for GO and GO-DA are highly similar, proving that the structure of the 2 samples are quite similar and that the reaction with maleic anhydride is not carried out. Maleic anhydride may not be able to enter the interlayer gap because toluene, the normally used solvent, inhibits this from happening. Figure 5 provides a possible explanation for the existence of such nearby protons. A COH proton is one layer may be very close to a COH or COC carbon atom in an adjacent layer due to the warped layered structure of GO, leading to the short contact time CP resonance. The frequency of COH or COC pairs is larger than that of COH or COH pairs, though because of steric restrictions. Figure 6 shows water molecules, which are rather immobile, are another potential source of very near protons. 2 carbons in the COC group may be impacted by a single near proton, but only 1 carbon in the COH group. The short contact time lines from the COC group are stronger than those from the COH group for both models due to the above reasons. Figure 7 shows each of the 2 1H NMR resonance produced by GO and GO-DA are at around 1.8 and 4.7 ppm. However, the former resonance in GO-DA is a shoulder. The lines at 1.8 and 4.7 ppm must be attributed to COH and H2O, respectively, because the tertiary COH group's 1H chemical shift is in the 1 until 2 ppm range.
In conclusion, solid-state nuclear magnetic resonance spectroscopy was used in this experiment to identify the presence of elements in graphite oxide structure. Graphite oxide samples were treated with different chemicals to get new types of graphite derivative. From the data given, it says that the bonds were relatively stable compared to the alcohol group that may condense to form ether linkage. The graphite oxide structure of the crystal has a long-range order where it has consistent pattern of particle arrangement that regularly repeats throughout the crystal structure. The alcohol and ether groups look homogeneous in proton and carbon-13 spectra due to the strong interaction from protons in trapped water molecules.
Here are some of the references we use.